Okay, well, welcome everybody to today's Philosophy of Physics seminar. It's a great pleasure to welcome a local today, Professor Iliffe, who is a Professor of History of Science here in Oxford. He's now been here a few years, and we've been talking about asking him to talk for a while and never got round to it. So it's great that we've finally done it and you're here. So Professor Iliffe is a expert on Newton. Since, I think, 1999, he established the Newton Project, this amazing online resource of all of Newton's works, and author of Priest of Nature and other works on Newton. But Newton's just part of it. He's written widely on early modern history of science, Enlightenment science, particularly in relation to religion. So, Rob, it's a great pleasure to have you here. Over to you.
Thanks, Oliver, and thanks for inviting me. I decided to give this talk really because George passed away 3 or 4 months ago, and it felt like a good time for me to gather some thoughts about George's approach to the history and philosophy of science. I met George in the late 1990s, and then in 2004 I spent a year at the Dibner Institute where he was the director. And then as the result of that, he and I collaborated on producing the second edition of the Cambridge Companion to Newton. And I found him to be a really generous guy. I'll give you a little bit about his biography. In fact, that'll be a key part of what I'm talking about later on. But I think he's made a signal contribution to aspects of the kind of bundle or family of approaches that come under history and philosophy of science. And at the end, I'll pose the question about whether his approach points the way to a kind of fruitful collaboration between historians and philosophers of science. George worked in a number of different areas of the history of science. He worked on the history of the electron. He worked on the history of geodesy. He worked latterly on the history of the measurement of constants, and that was something he was spending a great deal of time on in the last few years of his life. But as I'll say later on, he was actually spending a great deal of time, as he put it, becoming a historian and working very, very closely on specific Newton documents, specifically in the 2 to 3 years between late 1684, when Newton started thinking about what would become the Principia Mathematica, and early 1687, when Newton really finished working on what would be the Principia, published in the summer of 1687. So George's background, he's born in 1938. He has an extraordinary breadth of interests, and there's an interview that I rely on, I should say, that I've got in that I've highlighted in yellow for those of you that can see it, where I've simply and lazily taken what George said in this interview, and I'll read it because I think it tells you a great deal about George. But he attended Yale. He is interested in to begin with, he was interested in a wide variety of topics. He's evidently an extraordinarily talented person in many different fields. Interested in theatre directing, philosophy, modal logic, mathematics, of course, mathematical physics, political science. Most of his career was spent, and I think uniquely, as a philosopher, so working in the philosophy department at Tufts, but spending a great deal of time as an engineer working on turbine failure in nuclear power stations and jet engines. I mean, how many people combine those things? You're going to tell me that a number of people do. It's an obvious career path. So from the late 1950s, this guy was interested in a number of different topics at university, and he was simultaneously working for General Electric, spent a decade at Pratt & Whitney, working on futuristic jet engine design, consulting on failure analysis in jet engines. This is after, from 1968, from 68 to 2003, he was a consultant for a company in Cambridge, Massachusetts, working on turbine failure in a number of different areas. George went to Harvard in 1964 and came across Kuhn's Structure of Scientific Revolutions, which had only just been published 18 months earlier. It had a major effect on his thinking about the status of science and how akin it was to other human activities. I think in some of the writings he produced in the last 15 years of his life, he at least thought of his entire career in science as a response to some of the themes raised in Kuhn. He went to Tufts in the late 1970s and taught a course on social science and philosophy of social science, wondering or pondering, as one might, whether the latter was actually a science. But he said in a number of places he wanted to know what a science was. In his case, he wanted to know what the epistemic status of physics was before he could work out whether social science was a science. And of course, he went back to Kuhn. Kuhn raises the question and does as much as he can to show that science is a human activity just like any other. And I think George was, in his conversations with Kuhn at least, was, one could say, upset, I think, about the extent to which Kuhn had an influence on people, particularly students who claimed that science was an activity like any other activity. But of course, Kuhn's work raises the issue that is so crucial for modern historians of science, which is to say, once you've shown that there are indeed many similarities between the practice of science, scientific practice, and other human activities, you then have to say why it is that science is special, robust, and different. And those are the questions that guided George in a career of over 40 years. Before I go on, I did want to just talk a bit about the Principia, because this is about George's engagement with the Principia Mathematica. For those of you that don't know, maybe this is being condescending, but I'll say it anyway. The Principia was published in 1687 and appeared in two subsequent editions during Newton's lifetime, 1713 and 1726. Most of the editions we see refer to the last edition or to translations of it. Each edition has 3 books, following the definitions of key terms and the laws of motion. The first 2 books introduce mathematical propositions and deal with idealized situations susceptible to mathematical treatment, including abstract attractions, what Newton calls attractions, which become something different in book 3. The third book, The System of the World, provides illustrative examples of how the approaches adopted in the first 2 books can be applied to the real world. The second book deals with motion in resisting media. In subsequent editions, Newton adduced 3 rules of reasoning in the 1713 edition, and then I think crucially, and specifically or especially for George, the 4th rule of reasoning was added in 1726, but it's quite clear that the 4th rule of reasoning embodied something or expressed something that Newton had felt very deeply about from the beginning of his research into orbital dynamics. Newton started thinking about orbital dynamics at various points in his career. We don't have time to go into this in very much detail, but it's important to understand, and it was important for George to be aware of the status of Kepler's three laws in 1680 and particularly in 1684, when Newton started thinking about the relationship between an inverse square law and an ellipse, or at least he started to think seriously about it. What George wants to say in his writings is that there is a degree of comparative accuracy in terms of representing planetary orbits in a number of different theories that are current in the early 1680s. We may think that Kepler's three laws, they became laws after the Principia was published, but Kepler's three rules, we may think that they were well established by the early 1680s, but that's not so. There were competing theories, some of which embraced parts of Kepler and some of which deployed very different approaches to representing or explaining the orbits of planets. One of the issues, of course, is that measurements were, measurements to determine the ellipticity of the inner planets and Mars were at the bleeding edge, giving rise to very small degrees of ellipticity. And it's something that Newton grapples with in the 2.5 years that he's writing the Principia, as to how close the most robust observations we have of these planets correspond to the actual orbits of these planets. Because as we'll see, and as you know, these planets don't travel in ideal conic sections. From 1681 to 84, there were a number of discussions in London between Christopher Wren, Robert Hooke, Edmund Halley, and some others about the relationship between an inverse square law and the shape of planetary orbits, which were understood to be roughly elliptical. And famously, Edmund Halley visited Newton in the summer of 1684 and asked the question which has been variously understood by historians, but essentially it is, if you have an inverse square law, what is the orbit that results from that? You could say that actually the question he asked was the opposite, which is, if you have a quasi-elliptical orbit, what is the force law that governs it? 3 or 4 months later, after this visit, Newton published his famous short tract, a 9-page document called De Motu Corporum, or De Motu Corporum in Gyrum, which he sent to the Royal Society in November 1684. And it's, if you like, the embryonic seed of the Principia Mathematica. Over the following few months, he developed this into a much broader series of papers and had a kind of draft version of the Principia by the end of 1685 in the form of 2 books, which he rejected. And I'll show you images of these in a minute. But this is still far short of the extraordinary richness of the published Principia Mathematica in 1687. I think it's very important because I think lots of people don't realise that in these early versions of Principia, Newton is dealing with interactions between large celestial objects, not with an infinite number of interactions between masses of various sizes. So on the right is George Smith, and on the left is Isaac Newton. I wasn't quite sure where to put this image, but since this is about Smith's interpretation of understanding of the Principia, I wanted to juxtapose these 2 people. George attended a course given by Kuhn, who'd come to Harvard in 1983, and Kuhn was giving a course that or a version of a course he'd been giving for 3 decades or more, from Ptolemy to Newton, and suggested that George give a class on Newton. So according to George, and we have no other evidence to the contrary, he agreed, and he read the Principia carefully. And I have to say that George is one of the few people, and I think he is absolutely right about this, he's one of the few people since Newton wrote the work in 1687 He's one of the very few people who has gone line by line through Principia and checked the calculations. That's the kind of person he was. So he read the Principia carefully and ultimately developed an influential course at Stanford from 1986, which those people who now are, if you like, camp followers of George point to as being extremely influential in their career development. So remember, George is an engineer. I think he's an engineer first and foremost, and in his spare time he teaches Gödel and other things at Tufts. I'd been thinking hard about how evidence works for 10 years. I suddenly found somebody in front of me. That's not Kuhn, that's Newton. I found somebody in front of me, somebody who had not only seen everything I'd seen, laugh. This is an interview, and he's always laughing, George. But he was way ahead of me, and he was self-consciously asking himself how to get the highest quality evidence in physics. He says it in various places. He saw an opportunity to do what he had not managed to do with optics to the extent he had hoped. And all these years of thought about how to get high quality evidence and how to achieve the greatest evidence, combining mathematics with natural philosophy, so to speak, came together. And you know, there are 3 editions. They change from one edition to the next. That's instructive. And I'll come back to that at the end. For George, the pathway from 1687 to 1726, the refinement of concepts and the adducing of different kinds of evidence is crucial to understanding the Newtonian triumph or the Newtonian achievement. And of course, it goes on after Newton died. George, and I should say, for those of you who want an easy introduction, the Stanford Encyclopedia of Philosophy piece is a good intro to George's thinking about the content and methodology of the Principia. For George, the achievement of Principia, in terms of the applicability of the theory of universal gravitation to many problems, has been both understated and overstated. I won't have time to go into this in detail, but it's obvious that this is an extraordinary, stunning achievement, the book. It shocked people. People said to Newton, people who had no reason to genuflect before him, told him that he'd done something that was undreamed of. Other people said that he'd killed off natural philosophy because he'd invented it and perfected it at the same time. That didn't happen to be true. But as George points out, and this is in homage to people he built his work on as historians of science, Clifford Truesdell, Curtis Wilson, Howard Stein, and to some extent Bernard Cohen. The attention to Newton, his fetish for Newton, has really turned attention away from the unbelievable work that went on in his wake by people like Euler. Clairaut in particular is underestimated. I mean, his work is transformative in the middle of the 18th century. D'Alembert and of course Lagrange and Laplace. And though narrowly focused, I mean, the Principia does only deal with a very small part of the world. Its undreamed of success became an inimitable exemplar for doing science until the end of the 19th century. The methodology of the Principia is what George understood. By methodology, I think George understands something different from what philosophers of science have understood to be methodology, but we can discuss this. The emphasis in Principia is really that it is a kind of handbook. It's a handbook for doing science. It's a handbook for getting from apparent, relative, common quantities to the real thing, to mathematical, true, absolute quantities. And one moves from what he thinks of as, relative, fallible data that human beings gather through various processes to get closer to, if you like, the noumenal world that lies beyond beyond appearances. To do this, the great triumph of Principia is to develop concepts or entities that can have quantities attached to them. These are theory guided measurements. These are theory guided quantities, and I'll come on to that later on. Of course, this rules out for Newton, to the chagrin of most of his commentators. It rules out or defers for later consideration as mere hypotheses topics such as the physical nature of forces and the physical mechanisms by which forces act. It is not as crazy as it may seem for people to say, as they did, that what Newton achieved was mainly a mathematical triumph rather than a triumph in physics. Because if what you put forward is absurd, literally absurd, which Newton's work is, then why should you accept it? How can you possibly accept action at a distance in real time across an infinitely large universe? I mean, Newton was not concerned by constraints placed by the speed of light. I mean, in his world, objects at opposite ends of an infinitely large universe operate on each other in real time. That is absurd to his contemporaries. George's great discovery, I think, his great articulation is to say that in Principia, Newton's triumph is that every systematic discrepancy between observation and theory, no matter how small, says something about the natural world. This gives rise to a potential research strategy. It's not whether calculated locations of planets and satellites agree with observations, but whether robust physical sources can be found for each systematic discrepancy between those calculations and observations. As time goes on, there should follow closer and closer agreement with observation in a series of successive approximations in which more details of our solar system that make a difference become identified. The obvious exemplar for this is the discovery of Neptune. In a sense, everything follows. That is the standard example. But of course, there are numerous examples that are less known. But I think for George, much more interesting because they reflect on minor disturbances or minor problems that emerge from within Newton's theory that require correction of the theory. Whether it's the varied density of a planet or the surprising reach or extension of the gravitational pull of Jupiter or Saturn. Those are the things that Clairaut was brilliant at dealing with in the late 1740s and early 1750s. That's what allowed people to identify the return of Halley's Comet so accurately at the start of 1759. Again, that's another story. Again, so anything in yellow is, for those of you who can't see this, sorry about that, but for those of you who can, anything in yellow, with further apologies for the garishness. This is George in his 2020 interview. I should say that he was interviewed about 4 or 5 months after the pandemic started, and I'll say something about that later on, partly because George does. People who look at Newton don't look at it from the point of view of what the history of evidence in orbital mechanics has been. The standard view is, well, that calculation kept succeeding. In fact, from the time Newton published the first edition of the Principia until 1991, there's only one brief 25-year period. Depending on how you count it, it could be as much as 30, when there was no known discrepancy between calculation and observation in celestial mechanics. In other words, the evidence was coming not from agreement, but from disagreement. So for George, it's as if the production of these discrepancies, the search for these discrepancies, I mean, we can think of older styles of philosophy of science, but the search for discrepancies is a key part of what this branch of science is about. Once subtle but empirically verified physical effects have been identified through new observations or measurements, this feature is then incorporated into a new and richer mathematical model, which of course we see throughout the 18th century, with refinement of what we might call as the Newtonian theory of gravitation. Increasingly nuanced discrepancies arise in relation to a specific state of a model, so a specific moment at which Newton's theory is held to hold, that provides an idealized counterfactual account of the world, according to George, which he calls closing the loop. Closing the loop and repeating the process, yielding still smaller discrepancies, an increasingly subtle, more highly constrained source for them, provides evidence for both the theory and the previously identified details. The more times the loop is traversed, the tighter the error bands become on both the theory and the previously identified details, so that the evidence for the theory-based counterfactual conditionals delineating the differences these details make becomes ever stronger. There is a circularity, of course, in this process. Successful physical theories introduce novel quantifiable entities, according to George, force, mass, and law-like irregularities. Defending their existence at some level is a major goal of research. Success in discovering more nuanced effects resulting from the physical world indirectly confirms the core concepts and elements within the mathematical theory. So there are moments, of course, when aspects of Newton's theory of universal gravitation are contested, not the relationship between mass and force, but whether the 1 over r squared law holds exactly, or whether you need a 1 over r to the fourth element to be added. So these things emerge as crises at various points in the 18th and 19th centuries. This results in core elements and assumptions going explicitly untested, but a theory can continue to be tested decade after decade without it explicitly being said to be tested, because it's being presupposed in ongoing research and is, as it were, en passant being tested. That last bit is actually a phrase from a work by George. So in a sense, there is this indirect corroboration of the core elements of a theory as time goes on. I want to point to, this is an example perhaps of something that's amusing and illustrative of what George is saying in a way. This is actually Newton's own personal copy of his 1687 book, and on the right-hand side is his personal interleaved copy of his 1687 Principia. So these are two books that he had at his disposal to annotate. On the left-hand side, you can see that he's very unhappy with some of the accounts of Law 3. Again, George has written, I think, very, very perceptively about Newton's problems with the third law. But Newton himself had real problems with the formulation and the epistemic status of Law 3. He doesn't like, at various points, he doesn't like to every action there is an equal and opposite reaction. And he's crossed it out in his own copy, from probably the early 1690s, and then from his own interleaved copy, which were notes for the second edition, he's also crossed it out, as you can see on the top right-hand page. One of the things that I'll say as we go on is that these sorts of details were things that George decided he wanted to concentrate on in the last decade of his life, because he thought that his big approach, which I've outlined, could also bear fruit in looking at the most minute details. And that's the point where in this interview he says, of course with a laugh, because he's like that, I'm on my way to becoming a historian. Because I think that's what he thinks historians do, is just look at this kind of thing. It's not entirely true. For George, what's important about Newton, amongst other things, is his ability at dealing with quam proxime situations, what we call approximations in books 1 and 3, by dealing with conclusions that don't hold exactly but only approximately over limited periods of time. And George has written, again, I think very perceptively about this. The number of times Newton refers to quam proxime in the Principia is extraordinary, and George on a number of occasions has said, The fact that no one mentions this in the 18th and 19th centuries, or very few people do, suggests that very few people read it. And many of the great philosophers of the 18th and early 19th centuries clearly didn't read this carefully at all, or at least they didn't read these parts of the Principia that George did. Approximation expertise is required. Again, this is a big issue, and I'll point to this in a minute. But approximation expertise for Newton is required both because of human fallibility and also because the world is intrinsically intractable. And I should add, of course, that there's what George calls epochal and spatial parochialism, which is another way of pointing to the problem of induction. That Newton started off as someone very confident of his own ability to find exact truths about optics, mechanics, and everything else. And then gradually, as time went on, became slightly more of or at least there was a pose of humility that you see in Rule 3 and Rule 4 of Principia, where he's slightly more amenable to the idea that his theory of universal gravitation is true as far as we know. It's true now, and it's true as far as we can tell in the visible world, but it may not be true as time goes on. Measures taken by astronomers and others are always provisional. That's because the definitions in the first part of Book 1 of Principia tell you that we deal with relative common data, and we come together and we move approximately and slowly towards what we might consider to be an absolutely true view of the world. But of course, remember that the world, as we'll see for Newton, is not perfect. One orbit of a planet is never the same from one orbit to the next. So you have, if you like, epochal parochialism hardwired into the way the world works. And Newton is very conscious of that. So the measures taken by astronomers and others are always provisional and approximate and need constant revision through standard testing, through new theoretical prompts, or through improved equipment. And I do think George says, in conversation, George, of course, knows all this, but he wrote relatively little about the contribution towards precision that's given by improved instrumentation. And Newton deploys approximative reasoning very commonly in Book 3, which is the system of the world. That's the one that deals with the world that we actually live in, as opposed to a mathematically possible world. Here is the Rule 4 with a draft, which is one of George's two most significant texts from Newton, I think. In experimental philosophy, we are to look upon propositions inferred by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypothesis that may be imagined till such time as other phenomena occur, by which they may either be made more accurate or liable to exceptions. I said earlier on that, and I'll just briefly go through these images, I said earlier on that Newton had this wonderful process of moving from November 1684 to the start of 1687. This is a copy. On the left is De Motu Corporum in Gyrum. This is a copy of the first surviving draft that we have of Newton's initial attempt to solve the Halley conundrum. On the right-hand side is actually Edmund Halley's copy of this from shortly afterwards. This is a slight revise on the motion of spherical bodies in fluid. So this is a draft, if you like, of thinking about motion of spherical objects in resisting media. With, on the right-hand side, the first reference to leges motus, to laws of motion. And George, as I said, in the last few years of his life, was fascinated by the move from de motu to the Principia itself. De motu doesn't deal with universal gravitation. Universal gravitation is this massively enriched, generalized form of the kinds of approaches that Newton had adopted in de motu corporum. The main reason Principia includes so much beyond the de motu tract is Newton's endeavour to reach conclusions that had claim to being exact and true, despite the inordinate complexities of their actual motions. Now, the other text which George always refers back to, and I think is the key text for him, is an interesting one, because this is a pre-Principia text, and is found at the end of the De Motu Sphaericorum piece. It's called the Copernican Scholium, and it doesn't appear in any published work. I think it was first published in 1893. On the left-hand side, just to show you that there is some some manuscript evidence for this. All of the images are from Cambridge University Library, except the Trinity College copy of Newton's own 1687 Principia. This is an extraordinarily rich page, and it captures, I think George likes it because it captures everything that George is concerned with. So Newton, as far as George is concerned, Newton reveals in this his motivation for doing Principia type work, which is, in a sense, to find justifications for the Copernican system, which, of course, in the late 17th century is still up in the air to some degree. And so I provided a translation on the right-hand side. There are four elements of this that I think are worth pointing to very briefly. Newton says whether the planetary system is at rest or in motion, so we can call it a solar system, or we can call it any kind of system where you've got revolving planets. Whether it's at rest or in motion, so whether we deal with absolute space or relative space, its centre of gravity can be taken as the still. So we can consider it to be still with respect to the other bodies in the system, the still centre of the system, calculated in the body of the sun or very close to it. Hence, the Copernican system is proved a priori. The planets neither move exactly in ellipse nor revolve twice in the same orbit. So there are as many orbits to a planet as it has revolutions. Now, Descartes had gestured towards something like this, because vortices are always liable to changes in motion. So there is shifting, there are shifting orbits of planets. But Newton is introducing a new version of this with a new kind of mode of exactitude into natural philosophy. There are as many orbits to a planet as it has revolutions. This is because the orbit of a specific planet depends on the combined motion of all planets, not to mention the action of all these on each other. And again, this is a revolutionary comment which wasn't available in the published version. And then again, I think a phrase that George finds very important because it points to one of the very few times where Newton mentions or tries to deal with human fallibility. To consider simultaneously all these causes of motion and to define these motions by exact laws, allowing if convenient calculation, exceeds, unless I'm mistaken, the force of the entire human intellect. So even before universal gravitation, the multiple interactions of all these bodies in this system are so complex that no human being could ever exactly describe all of them. Or let me put it another way, no human being could devise an account that would deal with these motions over an extended period of time. And then the last bit is to say, because of the complex nature of the world, I think that this is something that George really does believe in. The world is complex. The world is extremely messy and complex because of the nature of the complex nature of the world. You're never going to get to an exact description of any planetary orbit or any state of the visible universe. Conventionally, the determination of the orbit of a planet has required a trigonometrical computation from 3 observations. But Newton says that's not good enough here. With what he has discovered, many observations from many different people need to be joined together and assigned to a single operation, which mutually moderate each other and display the mean ellipse. So again, the Principia is a handbook, or it's a set of techniques for finding an increasingly accurate view of the state of the world at one moment. So we go on to the late 1685, and this early form of Principia. It's in 2 books. On the left, you have the Liber Primus, Book 1, which he submitted as his lectures, Lucasian lectures for October 1684. And on the right-hand side, we have the Liber Secundus, the Book 2, which is actually the draft of what would become Book 3 in the published version. Here is the printer's copy of the Principia Mathematica at the very point when he's crossed out the earlier title, De Motu Corporum, and has got the new title on the top, which of course becomes the title of the book. Yes, that was a joke to myself. I'm fascinated by George's approach as an engineer. So this is a research question. I think George has himself generated a number of research questions about his own relationship to Newton and Principia. I think George's approach has revealed George's training as an engineer has allowed him to reveal many elements of Principia that no one has seen before. I think that's an extraordinary achievement. There is obviously a question of, if you like, interpretive subjectivism, which is what happens when your subject becomes too much like you, or you become too much like your subject. There's a balance. There's a point where you topple into finding that someone is just like you, or perhaps finding that someone is completely unlike you. But then you're not the best person who can tell when you reach that point. Newton's, this is George. Newton's proved more instructive to me than anybody other for my personal thing, other than my own experience as a failure analyst, where the experience you get as a failure analyst is you always subject your evidence to the most intense criticism, because if you're on something, the same failure is going to happen again. Okay. So I got taught to really scrutinize evidence. So by Newton, I got taught to really scrutinize evidence. Just ask yourself, what's the weakest element in this evidence? There are times in this interview where George speaks as if he's Newton, then they become, he's identified so closely with Newton. I think the interesting question is how productive that engagement is, and I think it is exceptionally productive. But of course, Newton was not an engineer. He was a natural philosopher introducing mathematical techniques into a natural philosophy that was being transformed by his own work. George is acutely aware that the evidence-producing strategies that are successful in orbital mechanics may not be generalizable to other fields. The 18th century is, of course, full of people like Hume, Condorcet, and all these others who wanted to be the Newton of their own field. You can't readily translate Newton's approach to other areas. It turns out there are vast swathes of natural philosophy, which we might call Baconian, which Newton's great achievements have no bearing on. The discoveries of flora and fauna and peoples in other parts of the world. Newton's great achievement has very little to say about them. Nevertheless, his training as an engineer allows him to see various scientific problems as similar. For example, climate change, and there's an interesting exchange with George on climate change in this interview. George says, and this is after a discussion about the introduction of AI into computational fluid dynamics. This is again the middle of 2020, so things are happening. I mean, I was already aware of GPT-2 in the summer of 2020, so George was aware of some of these new approaches to very, very complex systems. I don't know what's going to happen with massive analysis of huge data sets. We're watching it going on with pandemics, COVID. I've gotten preoccupied with climate science for an odd reason. I taught it for the first time in 1989, looking at it as an evidence problem. I tell my students constantly that climate change is a problem in risk management. I tell them then that we can't really establish causation for anything at the moment. And there's a nice conversation around that. And I discussed this with George actually when I was at the Dibner. George is interested in general, I think, in the longue durée. This is a response to Kuhn's question: what makes science different? Why is it robust? Why is it successful? Science lies in long-term community stretching internationally and through generations in a narrow specialty. Historians need to study that. It's where all the epistemic authority of science lies, in the constant rechecking of itself. Philosophers of science have been moving somewhat in response to the anti-science movement, but my disappointment at the same time, still looking not at broad enough periods of time, which is hard work. I mean, you really need groups to do that effectively. What bothers me now is the extent to which the authority of science has been lost in the US politically. It totally appalls me. So George's objection to certain kinds of local historicist analyses of texts is that it gives succor and tools to the anti-science movement. Studying the robust success of long-term major intellectual scientific fields is what will defend rationality as far as George is concerned. But George was also, as I've said earlier on, looking at those very manuscripts that I've shown you. And many of the most interesting things he's published that have come out posthumously, I think, are on very, very detailed local accounts of how Newton moves his theory, how he refines his notion of mass and force, how he does conical pendulum decay experiments to try and deal with Book 2, because Book 2, of course, as a fluid dynamicist, Book 2 of Principia is the thing that initially got George interested in Newton. So from mid-2020, I've been doing a great deal of manuscript work. I'm starting to believe I'm trained in history now. The manuscripts leading up to the first edition are instructive. I've scanned copies of his personal copies of the Principia. I'm not sure why he said that, because he could have got that online, but they're very heavily annotated. Then where he's making revisions or intending revisions, some of which he ends up not making, he's constantly thinking about how to strengthen the evidence. This is why George is really important. It's this constant focus on evidence. He's proved more instructive to me than anybody other for my personal thing. I got taught to, you already seen this one, I got taught to really scrutinize evidence. So George wrote a paper that initially appeared in a special issue of The Monist, I think, edited by Professor Guicciardini here, on his reflections on the relationship between history and philosophy of science. And it's an interesting one to look at. I'll leave you with a list of readings at the end. George was a leader of recent efforts to conduct historical research into the relationship between theory refinement and the marshalling of evidence, often in immense detail. I say that because there has been a kind of evidential turn in the history of science and in the philosophy of science. and it would be absurd to say that George has single-handedly driven that turn. But as part of that movement, he has, I think, introduced and informed the debate to a degree that few others have. And he's done it with a message for how to do good empirical research. So there's that kind of doubled relationship. You know, the good empirical research will inform our thinking about how evidence functions in science, and thinking about these things more abstractly, so more philosophically, will help historians do better historical work. George's approach has been inspirational for, I would suggest, a generation now of students working on how various fields constitute themselves as robust sciences. There's a lot of work being done on precision measurement, on the constant refinement of celestial mechanics at the end of the 19th century and the start of the 20th century. So there's a group of people who've published George's work, who've interacted with George. There's a big literature on what a great teacher George was. He published works with students. He published a book on Brownian motion with a student only 3 or 4 years ago, a student who's gone on to become a doctor. And he published a really significant piece of work on the electron, I think, in a work that Andy Warwick edited with Jed Buchwald some time ago. But he's also significant for historians working on more local or perhaps longer term cases where his work invites us to think about how both over a short period of time and a long period of time, evidence is collated, manufactured, fudged, or disputed. And again, George, I think, has an interesting, productive way of talking about how historians and philosophers science should be talking to each other. And he points the way forward for a viable and possible field of history and philosophy of science. One of the things, there are a number of implications of George's work. I'll just briefly mention two. I mean, one of them is George resolutely focuses on a particular version of Newton's science, and I think it's possible to use George's work to think more broadly about Newton, about how Newton's work is related across all of his endeavours. And we can do that because of the Newton Project, which is something that I started with Scott Mandelbrot more than 25 years ago, which is an effort to publish all of Newton's writings, everything he ever wrote, every dot, every cross T, every I. And it's an interesting research question as to where this comes from in Newton. We know that at the same time that Newton was doing the things I've been talking about, he was, as he saw it, solving the problem of the history of the world. Now you can, you may ask yourself which he took to be more important. I think he took both to be equally important, because one of them is trying to understand the history of the world and the true meaning of the Bible, and the other one is trying to understand the language in which God inscribed creation. They're both perhaps of roughly equal significance. But we, in the Newton Project, we haven't yet transcribed or done an edition of the Principia Mathematica. And we are hoping to do that in the next 2 to 3 years. Newton died in 1727, so it would be very nice to have a full transcription of all of the Principia materials online by the end of 2027. I probably said he died in 2027, as I normally do, but he didn't. He died in 1727. So it's 300 years since he died. And people the world over will be, provided we don't have cybersecurity issues like we've been having, people the world over will be able to see images of all of Newton's writings provided by Cambridge Digital Library, alongside transcriptions. They'll be able to use the transcriptions to search. They will have access to all of commentaries on Newton, all of Newton's marginal annotations. We will try and translate Newton's Baroque geometrical notation and approach into a more modern analytical mathematics to make it more accessible, paradoxically. And we hope it will be something that's a tribute to a number of people. One of the things that it will enable people to do is precisely the kind of detailed work looking at Newton's evidence base, the way he collated fudged evidence, which is something that, again, has been broached, done very successfully by George, but which can nevertheless be done perhaps much more in a much more enriched fashion if people have access to all of the data. Those of you who want to look more closely at George's legacy, there's a very good book published, edited by Marius Stan and Chris Smink, 2023, which has got a good introduction by the two editors and some very good papers in it, including one by George. It's the one on history and philosophy of science. It's freely available online, or at least it was to me. So please look at it if you get the chance. And at the end, for those of you who can see it, is a brief introductory reading list for George's work on the Principia. Thank you.